All right. Hello, everyone. I'm Bernd, and today is day 19 of Advent of Codes. Today's puzzle I thought quite hard again. It took me a while to get through it, but let's have a look. So today is about robots collecting material, and different robots collect different material, and we want to maximize the amount of geodes we have at the end of a certain time limit. So our input will be something like this. So we start with one ore robot, and they collect one ore at each time. So each robot will collect the corresponding material. And then we have prices to buy or to produce more robots. So we can get one more ore robot for 4 ore. We can get one clay robot. This costs us 2 ore, and so on for different materials. We have different prices. And yeah, we have 24 minutes. Each robot collects one corresponding material each minute. And at the end, we care about the amount of geodes we can collect in 24 minutes. Okay, let's have a look at the code. So there's quite a bit stuff we need to read and define the data. So for example, we find an enum with all the materials. We of course need to read the line and split it into files. And then we want to process the text so that in the real input is all one line. And then we get all the integers in this one line. And then we define all the costs. So we have, for example, for the material ore, the costs will be vector, or this all materials class, where the ore amount is set to v1. So v1 will be the first integer starting with 0. So that will be 0. That's given as the ID. And then this will be the integer at index 1, which tells us how many ores it takes to get one ore robot. Similarly for clay, we need 4 robots, so 4 would be V2 here, and then similar for the other materials, we need ore and clay and ore and obsidian, and so on. And we'll put that into the dictionary, and then we do that for all the blueprints of all this kind of strings. Okay, yeah, so I also already mentioned this old materials class. That would be to access a specific material more easily or more readably. So we'll have these types of materials, ore, clay, obsidian, and geode. And we can have our property as a tuple will be useful, and we'll define this operation. So we want to add two together. We might want to multiply one of this class with an integer. We might subtract some. And we want to also have a lower equal operation, which just compares the element-wise lower equal between one all materials class and another. And we can also map our enum to the corresponding all materials class. Now to solve the problem, what will be useful is an upper bound and a lower bound for the number of geodes we collected at a particular state. So if you have a current time and the current set of materials and the current amounts of robots, what we will do is for the upper bound, I will go through all the robot types, or material types, and for the cost to build a robot of such material. Then if we can afford it, so the cost is more than equal to the materials we have, we'll add the robots we add one of those robot kind to our robots, and then we go for data contracts. So importantly, in the puzzle itself, we're only allowed to buy one robot per round. We ignore that here, and also we conveniently forget to pay the costs. So that's why this function will give an actual upper bound. And yeah, in each step, a lower bound is kind of similar. So again, we go through each time step from the current time to the end. And we check if we can afford, but this time we want to afford just a geode robot. So that will be the cost. And if we can afford it, we pay the costs, we add one robot of those geode kind to our robots. And yeah, we also update the material based on the number of robots we had. So for each material, we get one more of it for each robot we have of that material. So that's definitely that will be a lower bound, because buying geodes as early as possible is optimal. And yeah, that's just one particular strategy we can do out of all possible strategies. But it might be better, for example, to buy a different robot first. But yeah, we'll not consider it here, so it will be a lower bound. Okay, then we want to get the maximal number of geodes possible. So there we'll keep track of materials, which will be and the robots, and we start with one ore robot. What will be useful is to consider this maximum ore required. So since we can only buy one robot in a round, we don't need the crazy amount of ore per round. So in particular, the clay contract, the obsidian contract, and the geode contract have a specific amount of ore we need to pay. And we don't need any more than the maximum of those per round. So if we have that many factories, it's not worth buying another one. So that will be useful in reducing the number of cases we need to consider, or states. And yeah, then we start with the first state, and we iterate through time. And in each round, we take the next states from the current round and make them into current states. And before we do that, or while doing that, we also eliminate strictly worse states. So we go through all pairs of state, and if one is strictly worse than the other, we kill it. So that will be also help us to reduce a few states, which means we don't need to consider as many, and the program will be quicker. Okay, then we'll refill the next states. We go through all the current states that will consist of material, robots, and history, which we can use to print what the runs, or like the states, what happened, how we get to states. We'll calculate our upper and our lower bound, and then we might improve the best result if the lower bound is higher than that. And if the upper bound is at most as big as the best result, we know that this particular state will not result in any improvements, so we don't need to consider it and not consider further states derived from it. Then we need to consider different things. So what we can do is either do not build a robot at this time step. So in this case, we just append this state to the next state. So the robots will stay exactly the same, and the materials will increase by the robots, because for each material, for each robot we have of that kind, we will add 1 to the number of materials. Okay, and then we go through robot kind and the costs in our factor costs. First, it will come useful to have this max ore required. So if the number of robots for ore are already equal to the max ore required, we don't want to buy another one. So if the robot kind is also ore, we won't add this to the states for the next round, and we continue. And then if we can afford it, so if the cost is at most of the materials we have, we'll append the corresponding next state corresponding to buying one robot of this kind to our list of next states. So then what will the next state be? So the material will have the old amount of materials where we have to pay the cost for the robot, and for each robot we'll collect materials. So that will be the number of new materials, and then the new number of robots will just be the old number of robots plus a robot of the particular kind we just bought or produced. And yeah, we can also add some history where we add the robot kind to history, which is not important for the problem itself. Okay, so yeah, that's the main iteration. Go through states and define next states. And then after the total time number of steps, we'll have a best result, which will be the best result achievable because we went for all possible states. When we do this eliminate strictly worse states, how do we do that? Which is quite important to speed up the program. So we have a list of good states which we want to fill, and then we iterate through the states, and twice we get tuples of states, and we don't do it for all the states because to not make it too expensive computationally. And then we first check if the two states are exactly the same. In this case, we don't wanna delete one of the states, so we continue. Then the next case is if they're different and the materials of the first state are at most we have as many materials as in this other state, and we have as many robots as in the other state. then that means the first state is strictly worse than the second state. And yeah, if it's strictly worse, and at the end we only use states which are not strictly worse than another states and append that to the good states. That helps, yeah, gets rid of some states. We don't need to consider as many paths in up here. So that with that we can solve the problem. So we just process the lines and get the blueprints. Then for each, then we get that gives us the that's exactly the factory costs. And then we just for each kinds of factory costs, we get the maximal geodes we can get, and the solution will be this number times the index. Yeah, so we can run a little test. It takes a little bit, but with a bit of luck. Yep, that looks good, nice. So that worked out. So it also takes a bit to run on a real input, but it also gives us the right solution, which is nice. And then next for part 2. So part 2 has a small change, which is that we do more time steps now. So we allow for 32 minutes and want to get the most geodes in these 32 minutes. So the program is mostly the same. We use a lot of things from part 1. There's one extra change which helps accelerate things. So and this is in this eliminate strictly worse states. So here we again consider for each state and each other state, if they're the same, we don't want to say that one is strictly worse based on that. But if that's again, if the first state is worse or is almost as big as the second state, and it's not equal because otherwise we would have continued, then that makes it strictly worse. But there's another way which a state can be strictly worse than another. And this will be given by this. So as we mentioned, if we have the max ore required, if we have that many ore robots, then we don't need any more ore robots. And similarly, then also the amount of ore we have collected does not matter. So if the first state has less clay, less obsidian, less geode, and less robots than the second state, and the second state has already the maximum amounts of ore robots that we need, then we can also call the first state strictly worse. And we need one more condition actually, that in this very first round, both states can buy the same amount. So we need that or at least the second state can buy more. So we also need that in this particular round right now, the other state has enough ore material. So it needs, in particular, it needs more than the max ore requirement, ore material. And if all these conditions are fulfilled, we can as well say, or can again say, that the first state is strictly worse than the second state, and we cannot consider it part of the good states, which also helps speed up things a bit, I think. And then the way we calculate the solution is slightly different, and this time we just multiply all the results together and we only do it for 3 of the blueprints. And yeah, I think that also runs for a bit, but it does eventually give the right result for both test input and the real input. And yeah, that was day 19. I hope they enjoyed it, and best of luck for the future. See you around.